Let's talk about Z-scores. A Z-score is a score which allows us to standardize different kinds of values based on the mean and the standard deviation. It lets us compare different kinds of values, and it lets us determine what would be significant and what wouldn't. A Z-score measures how many standard deviations a particular value is from the mean. With a normally distributed data set, we consider the mean to be 0 and the standard deviations are each 1, a distance of 1, because it's the number of standard deviations. So this would be 1 standard deviation, 2 standard deviations, 3 standard deviations. Going in the other direction, we'd have -1, which represents 1 standard deviation below the average. Here's our average. -2 standard deviations below the average. -3 standard deviations below the average. So the Z-score of the mean is going to be 0. And the standard deviation of stuff that's in Z-scores, that's been standardized as Z-scores, would be 1. And this lets us have one way of computing all the different possible probabilities for different Z-scores. Instead of having to have a different table for every possible situation, which would basically be impossible. Using Z-scores basically let people calculate the number of standard deviations and how extreme a value was for anything using a table that standardized it before everybody had a computer in their pocket or on their telephone. In any case, we still use Z-scores. Basically, the Z-score is the number of standard deviations away from the mean that a particular value stands. If your Z-score is positive, then the value is above the mean. If it's negative, the X is below the mean, which I mean, if you know what the X value is and you know what the mean is, you could tell that quite easily. On the other hand, if you're just given the Z-score, then you can tell whether it was above or below the mean. Z-scores have no units. They normally round Z-scores to 2 decimal places. Lets us determine if a value is significant, if the z is greater than 2, or if the z is less than -2. If it's up here or down here, then it's considered sufficiently extreme to be statistically significant. That means it lies outside 95% of the values. Approximately 95%, recall, is going to lie between plus and minus 2 standard deviations. So if it lies in that other 5%, either 2.5% above or 2.5% below, then that is sufficiently extreme for it to be considered very unusual and statistically significant. One of those, whoa there, let's pay attention to this kind of deals. The formula to calculate your z-score for any particular number, you have to know the standard deviation, and you have to know the mean for that sample or population. If you know for the sample, then you take the x value that you're dealing with, you subtract the mean for the sample. So you're finding out how far it is from the average. And then you divide by the standard deviation for the average. Or if you happen to know the statistics for the population, then you would subtract, you'd write it like this. You'd say mu for the population mean, and then sigma for the population standard deviation. Suppose we had a situation where the mean is 5 and the standard deviation is 2. And we wanted to know how many standard deviations away from the mean is, I don't know, let's say 8. Well, 8 is 3 units above 5, right? Because we know 8 minus 5 is 3. How many standard deviations is 3? If 2 is 1 standard deviation, so 4 would be 2 standard deviations. 3 is 1.5 standard deviations, right? Well, you divide by the standard deviation, and that tells you how many standard deviations this distance from your number to the average is. So this is where the formula comes from. You get how many numbers your number is from the average, and then you divide by the standard deviation to find out how many standard deviations that is. Look at ACT scores and SAT scores. These tests both measure similar things. They're just standardized test scores. But your typical SAT score is going to be in the hundreds. Your typical ACT score is going to be in the teens to 20s, kind of like between 10 and 30. I've never seen one as low as 10, and I've never seen one as high as 30. So these are in 2 digits. These are in 3 digits. A 30, like I said, would be out of sight high, genius in an ACT, assuming it's even possible to get a 30 on the ACT. A 30 on the SAT is lower than it's even possible to get. I think if you sign your name to the test, you get a 200. So how do you compare these? Well, you look at their Z-scores. You compare the Z-scores of the two. Okay, so I'm just going to throw out some numbers. I don't know exactly offhand what the averages are anymore. I think I did at one time. But let's say that the average on the SAT is 20. And the standard deviation is 5. And let's say that the average on the SAT is 600. I think that's going to be really off. And the standard deviation is 150. So how would a test score of 28 on the ACT compare to a test score of 800 on the SAT? And remember, don't hold me to these. I'm just throwing out some numbers vaguely from what I remember. Okay, so your Z-score here is going to be, you start with your value, you subtract the mean and divide by the standard deviation. So this would be 8/5, which would be 1.6. So if we look now here at the Z-score for this test, we would have 800 minus 600 divided by standard deviations 150. So we've got 200 divided by 150, which is 1.33. So the 28 on the ACT would be a better score than an 800 on the SAT, if these numbers are right. Don't hold me to that. But you see how it works. Now, next question. What numbers on the ACT would be significant? In other words, at what point would we say somebody was a genius or So let's just look at the high and low numbers for this. Now, significant is considered to be more than 2 standard deviations away from the mean. So if the Z-score is greater than 2, or if the Z-score is less than -2, that's considered significant. Well, what if we said, looking at this formula, we've got Z equals X minus mu over sigma, right? What if I put the 2 in for Z and I'm looking for the X value? So it's going to be X minus, what did I say, 20/5. If I solve this for X, I'd want to multiply both sides by 5. So I've got 10 equals X minus 20. And then if I add 20 to both sides, There's my 30. So if X is 30, it would be considered extremely high, up in the top 2.5%. Remember, we looked at the standard curve. Above 2.5%, the top 2.5% is significant. The bottom 2.5% is significant. And those are cut off by being more than 2 standard deviations away from the mean. If I set this equal to -2, if I said -2 is equal to x minus 20 over 5, and then I multiply by 5, and I've got -10 equals x minus 20. Again, I'm going to add 20 to both sides. So that would be 10 equals x. So a 10 would be in the bottom 2.5%, and a 30 would be the cutoff for the top 2.5%. So the answer here is if x is greater than 30 or x is less than 10. All right, so we will be using Z-scores a lot more when we get to chapter 6. This is just to give you an idea of how they work. They're not that hard. It's nothing but the number of standard deviations away from the mean.